Hey, what's up, guys? Today we're going to be talking about waves. Now, you're probably thinking that we're going to be talking about the waves that are in the ocean. But although those are a type of wave, they're not the type that we are going to be looking at. So, waves such as microwaves, the kind that heat your food in a microwave, radio waves, the waves that allow you to talk on your cell phone. These are also types of waves, right, that produce or carry energy, but we can't actually see them. So we're going to focus on two different types, and they are transverse and longitudinal. So first, looking at transverse waves, over on the left, you can see a simple picture of one. So transverse waves are unique in that the particles move up and down, or perpendicular. So you can see right here we're moving up and then back down. So transverse waves actually look like the waves that you see in the ocean. Then longitudinal waves, right? They're unique in the particles move side to side or parallel. So looking at the picture, you can see that the wave is carrying the energy to the right. Right? So that is the main difference, or the one distinction that we make between the two. So we can identify different parts of each wave. Starting with a transverse wave, we can first identify what's called a resting point, or sometimes a stationary line. So it is the line that runs directly through the middle of the wave, right here. So it divides the wave up into equal halves. You have the top half and the bottom half. So top, everything up here, everything above the middle line, and everything below the middle line down here. Right? And it divides it up equally, like I said, so the dimensions or the sizes of the parts of the wave on the top are the same as on the bottom. The wave is symmetrical. Right. Next, we can identify what's called a crest on a transverse wave. So a crest is the highest point of a transverse wave. So if you look, we have a crest here, we have a crest here, we have a crest here, and we have a fourth crest over here. So crest, the highest point. Think about a mountain. There's a crest on a mountain that is at the very top, or the peak. Right? So on any section of a wave that you're going to look at, there are going to be multiple crests. And crests are important in that we use them as kind of reference points when we're measuring different parts of a wave. Then, the opposite of a crest is what is called a trough. So a trough is going to be the lowest point on a transverse wave. So you can see we have a trough down here, trough here, and we have a third trough over here. So trough, lowest point, if you're familiar with a trough that farm animals drink out of or eat out of, it kind of looks like that. That is basically the shape of the container that they feed out of. If that helps, then by all means use that example. If not, just remember trough is the low point, or the bottom of the wave. Right. Then, wavelength. So to find the wavelength of a transverse wave, you simply measure from one crest to the next crest. So for instance, if we were to measure from here, right in the middle of the crest, to here, that would give us the wavelength of this section that we're looking at. That says wavelength. We can measure also from a trough to a trough. So from here, right, one trough to the next trough. Right? They have to be consecutive troughs. So we can also find the wavelength down here. Right. Next, we have what's called amplitude. So amplitude kind of means the same thing as the height of a wave. So to find the amplitude, we measure from the stationary line, or the resting point, the line in the middle, to either the top of a crest or the bottom of a trough. It doesn't matter, you can measure either way. So we can start here, measure to the top of a crest, or start on the line, measure to the bottom of a trough. Right. The numbers that you get from there and there are going to be equal. Like we said, the wave is symmetrical. So both of those lines would be measuring the amplitude of the wave. So the amplitude, or the height of a wave, describes how much energy the wave is carrying. So if you have a wave that has a high amplitude, the waves are very tall, there's a large distance between one crest and one trough, and it's going to be carrying a lot of energy compared to a wave where the crests are short, or there is a short distance between a crest and a trough. Alright, another property that we can identify when looking at transverse waves is what's called frequency. So frequency simply describes the number of waves produced in a given amount of time. So we're always looking at a section of a wave, a portion of a wave. Waves extend a long distance. So in this particular wave, we're looking at a section that occurred over a 5-second time interval. So we have two waves that we're looking at, wave 1, wave 2. But like we said, both occurred over 5 seconds, so that's going to be constant or equal. So looking at the two waves, we say that the first wave has a low frequency and that the second one has a high frequency. So how do we determine which one has a low frequency and which one has a high frequency? Well, you can simply look at it and tell. You see more crests and troughs in wave number 2, so that's going to tell you that more waves pass through, giving it a higher frequency. Wave number 1, you don't see very many crests or troughs, so the frequency is low. Right. Now, to measure it accurately, to be precise, what you do is you measure from the bottom portion of a trough. So we'll start at the resting line, at the middle point there. From there to there, right, kind of where we started. So you made a complete pass. You traveled to the top of a crest, and then all the way through the bottom of a trough back to the beginning. That's what's called a complete wave, right? A crest and a trough together, they make a complete wave. So you count the number of complete waves. So there we would have 1. All right. Then starting where we left off here, we would have a second complete wave. Sorry, apparently my dog wants to say hello. So from here to here, that would also be a complete wave. So we have 2 complete waves in wave number 1, or 2 complete cycles, you could say. The last portion of the wave there, we can see a complete crest, but we don't have the trough below, so we don't consider that to be a complete wave. So if we were trying to find the exact frequency of wave number 1, looking at the bottom, there's the equation. So number of complete waves divided by time. So the number of complete waves, we said, was 2. Divided by the time in seconds, which for both of them was 5. Right. Gives you the frequency, and the units that we use for frequency are called hertz. So 2 divided by 5, you can check my math, but I believe it is 0.4. Right. So the number of complete waves divided by time gives you the frequency. Next, the other type of wave that we're looking at is called a longitudinal wave, and we said longitudinal waves move side to side, right, or horizontally parallel, right, however you want to think of it. So the parts of a longitudinal wave that we identify are compressions and rarefactions. Right? So a compression is a section of the wave where the particles are all bunched up or pushed together. So right here in the middle of this area would be a compression. All right. Over here, this would also be a compression. So anytime you see the particles or the spring kind of bunched up, that's going to be a compression. So compression there, compression there. So like for the transverse waves we looked at, we saw several crests and troughs, or multiple crests and troughs in this section of the wave. For longitudinal waves, we also see multiple compressions and then rarefactions. They're very similar, crests and compressions and troughs and rarefactions. So the rarefactions are the portions of the wave where the particles are spread apart. So here would be a rarefaction. And then this space right here would also be a rarefaction. You can read that. So particles are spread apart, right? Then wavelength. We can also find the wavelength for a longitudinal wave. And we do that by measuring from one compression to the next compression, or one rarefaction to the next rarefaction. So if we looked at the compressions we labeled, so from here to here, that measurement would give you the wavelength. Then we could also measure from rarefaction to rarefaction. So from, get a different color here. So from here all the way over to here, right? That would also be the wavelength. The number that you get would be the same for both measurements. Obviously this isn't a perfectly drawn wave, but in the real world it's going to be the same. So that is how you find the wavelength of a longitudinal wave. So to kind of recap what we talked about, we said there are two types of waves that carry energy, transverse and longitudinal. We also said transverse waves move the energy particles up and down, or perpendicular, and that longitudinal waves move particles side to side, left to right, parallel, right? We identified the different parts of a transverse wave. The crests are the high points at the very top, the troughs are the low points at the bottom. The resting point, which runs directly through the middle of the wave, divides the top and the bottom halves equally. We found the wavelength by measuring from the center of one trough to the center of the next trough. We said that you can also find wavelength by measuring from a crest to another crest. Then amplitude, or the height of the wave, is measured from the resting point to the top of a crest, or the resting point to the bottom of a trough. Right. Longitudinal waves, the parts we identified were compressions, where the particles are all bunched up or compacted, and then also rarefactions, where the particles are spread out more or pulled apart. So we measured wavelength for longitudinal waves by measuring from the center of one compression to the center of the next compression. And also, we said that you can measure from rarefaction to rarefaction and that you will get the exact same number. So for transverse waves, ocean waves are an example of transverse waves. If you look at them, they look like ocean waves. They move up and down. So if you've ever taken a rope and kind of flicked your wrist up and down, you simulated the movement of a transverse wave. Longitudinal waves, if you take a spring or a slinky and kind of push it back and forth, you're going to see the energy of the wave travel through the slinky, and parts of the wave or parts of the slinky are going to bunch up, and then as the energy travels down the slinky, it's going to spread apart and bunch up and spread apart. So sound waves are a good example of longitudinal waves. So next time we're going to be talking about how the different parts of the waves kind of interact. How if you change one part, you increase, let's say, the wavelength, how that affects the amplitude or the height of the wave.